Hi guys, I just recorded this whole lesson with no audio, so I am coming back to do this again. So we're on day 2 of exponential functions, exponential growth, and exponential decay. And today we're going to hit the application portion of this, but first we're going to review. And we're actually going to see and dig a little deeper into what this b value is. So let's start with a warm-up. Recall that the exponential growth and decay function is y equals a times b to the x, which you'll be able to see in more application today. So the first one, determine if the following represents exponential growth or decay. So let's take a look at the b value. In this case, our b value is 1/4, and that is less than 1. So remember that when it's less than 1, we know this is exponential decay. In number 2, our b value is 1.25. And since that value is greater than 1, this is exponential growth. So now digging deeper into this formula, this equation for exponential growth and decay. We're going to look separately at growth and decay functions with their own equations. So the exponential growth function, that is this formula right here. Y equals a times 1 plus r to the power of t. This is technically that same b value, but now we're breaking it down since we're going to start dealing with rates. Rate increases and rate decreases. So in order to see that more clearly, we separate it with 1 plus or 1 minus. 1 being 100% of a starting amount, and then r being how much is that increasing by. 100% of your money is going to increase by 1% each year, depending on the bank account or the savings account you use. And so let's break that down. Let's see what each piece means. So A, that number in front, is that starting amount. So maybe you opened a bank account and put $10,000 in there. 1 is going to be that 100% of your money. R is going to be the rate of growth in decimal form. What that means is if I said the amount of money I put into the account is growing at 2% each year, we will not plug in 2 into R. We're going to plug in that decimal form. To get the decimal form of a percent, we do the percent divided by 100. And in this case, if you do it in your calculator, you get 0.02. If you're used to just moving your decimal place over twice to the left and putting the new decimal place there, that's fine too. Whatever gets you to a decimal form, not the percent. And T represents time. How many years are you putting your money into that account? That's the exponent right here. Everything together inside the parentheses, that b value that we talked about the other day, that whole thing's the growth factor. But today we're going to look at the rate of growth or the rate of decay, and that's the r value as a percent. Same thing for decay. The only difference is since something is decaying, we say that 100% of our initial amount is decreasing. It's being subtracted by a rate. So here's an example. Those values are from the first time I did the video, but now they're there. So number 1 says, identify the initial amount, the rate of growth, and then evaluate when t is equal to 5. So, in the first one, your initial amount is the number in front of your parentheses, that coefficient there. So for part A, I'm labeling it as part A. The initial amount, A, is equal to 50. The growth rate is what we're adding, since it's a growth rate and there's a plus sign. What are we adding to 1? We're adding 0.25, but it says as a percent. It's a rate of growth. So to go from decimal to percent, I'll do that on the side here. We multiply by 100. and we get 25 or 25%. And C says, evaluate when t equals 5. So in your calculators, just to show you what you would type in, it's that top line, 50 times 1 plus 0.25, whoopsies. To the power of 5, you'd use the caret key right here, to the power of 5, is equal to 152.58. And we round to the nearest tenth, so 152.6. In this case, for your calculator work, I'll show you in a moment, but let's do part A and B. The initial amount is 172. The rate of growth is this piece right here and written as a percent, so times 100, we actually get 30%. And when we plug this into the calculator with t equaling 5, we get 638.6. Remember, round it to the nearest tenth. This one's a little different. I don't see a 1 plus or a 1 minus in my growth factor. So I can't really see the rate unless I know what I added to 1. So really what's happening here is something's being added to 1, a rate, right? So to find that rate, it's easy to see in this case, but you can always just do 1 minus what they give you, and you're going to get negative 0.75, but we take the positive version of that. And now remember, we need to get it as a percent. So that percent, that's the part B question, would be 75%. And part A, the initial amount, is going to be 1,000. Part C, when you plug in 5 for the number of years, is 16.4. Okay. Now we're going to take this a little step further and look at a couple applications. We're going to look at basic applications and get into it a little more. So the first two problems just say, what is the function that represents this situation? We're not solving anything. We're just writing an equation for it. So let's label our parts. We know that this is the equation right here. And I put a plus or minus because we know that in these situations, you're either going to see a growth or you're going to see a decay. And when it's a growth, we add. When it's a decay, we subtract. The key word that points out to me in this first one is increase. So we're going to add. Let's label everything else. We don't have a final amount, y. We're trying to find that if they asked us. So the function for this, we're using the initial amount, A, which is the $100,000 being put into the account. Those profits increase by 1.9% each year. That's your rate, but be careful because we have to plug it in as a decimal. So I know it looks like a decimal now, but this is still a percent. To make it a decimal, remember we divide by 100 and we get 0.019. Very common mistake is for students to see the decimal and say, oh, it's already a decimal, but it's a percent. You want to change it. And now let's create our formula. Y is equal to the initial amount, 100,000, times 1 plus the growth rate, 0.019, to the power of, that should say t. T would be the number of years you have your money in that account. Number 5, I see the word decrease. I know we're looking at exponential decay. That starting amount A is equal to 41,000 students. The rate is 0.07 because we want it as a decimal. And our final function will be y equals the initial amount, 41,000, times 1 minus, since it's decreasing, 0.07 to the power of t. It says the number of food trucks, which, by the way, are the best thing in the world. If you've ever been to Rutgers or had food from their food trucks, they are the best. And they have food truck festivals these days, which are even cooler because they have so many different types of food, which is awesome. Hopefully those open up sometime soon. But yeah, so they're looking at food trucks that in a city have been increasing by 50% annually in a city. There were 2 food trucks in the year 2010. Write an exponential growth function, just like we did, that represents the number of food trucks to years after 2010. So 2010 isn't the starting amount, but it's telling us that's the starting year. So let's ask yourself, how many trucks did we have in that starting year? Our initial amount A, in this case, will equal the 2 trucks we start with. The rate of increase is 50%, and as a decimal, that's 0.5. So the function will be y is equal to the initial amount 2 times 1 plus 0.5, because it's increasing, to the power of t years since 2010. How many food trucks will there be in 2030? Well, we have to think about time here. We're not plugging in the year because that's what they give us. It started at 2010. Now it's 2030 that we're looking at. How many years passed by? In this case, 20 years has gone by from 2010 to 2030. So all of this information stays the same. We added the t equals 20, and now we're actually solving. How many trucks are there going to be, and is it reasonable? So let's see. Y equals 2 times 1 plus 0.5 to the power of 20 years. What does that equal? Calculator. Show you how to plug it in. 2. Let me clear everything. 2 times 1 plus 0.5 caret key to the power of 20 years. And we get 6,650 trucks. Rounded up, I would say 6,651. So your final sentence should say, there will be about 6,651 trucks in the city. Now, does that make sense? Really, it depends. How large is this city? Because 6,651 trucks is a lot of trucks. That's really up to you. You guys put your reasoning down. A city can be very large, and if a city really likes food trucks, they can have that many food trucks. But is that likely? Probably not. Not right now, no. Okay. So just write that down. Does this sound reasonable? I'm going to say yes. If a city loves food trucks. All right. I'll do a couple more review problems with you guys. We already learned this, but let's review it. This says find the initial amount and the rate of decay, then evaluate the function when t equals 3. I'm going to at least, so you guys can do this part, evaluate when this t is equal to 3. I'm going to do number 9 and show what the initial amount and the rate of decay is, because I don't see the 1 plus or minus here, so it might trick some of you. So here, your initial amount, A, is the 550. What are you subtracting, since it's decay, from 1 to get that 0.4 inside? To find that out in your calculator, just do 1 minus 0.4. You're going to get 0.6, and that's what they decreased 100% of the initial amount by. So when you guys answer part B, remember as a percent, the rate of decay is 60%. You can multiply that number by 100 to get that. Okay, and that's it. You guys will do that last part on your own. Let's do these tables real quick. It says determine if the table represents growth, decay, or neither. They don't ask you about linear, so you don't have to check if you're adding or subtracting by something each time. You just have to check that can you multiply by the same number each time to get to the next. And if it's greater than 1, it's growth. If it's less than 1, it's decay. So in this first part right here, I notice that you actually multiply by 3 each time to get to the next number. So that's exponential growth, because 3 is larger than 1. Remember, if you don't know what you're multiplying by each one, go backwards. What's 25 divided by 50? Or what's 50 divided by 100? If you do those in your calculator, you're going to get 1/2 for both. You're going to get 1/2 for all 3. So what that tells you when you go backwards is technically, what are you multiplying by each time? So in this case, we're multiplying by 1/2 each time. And that is an exponential decay because 1/2 is smaller than 1. All right, so that's it. If you have any questions, feel free to email me.